All right, hi everyone. We are going to continue the proof methods. And so today this is proof by cases. So this proof method is used really frequently with either or statements simply because in that situation we have several cases that can occur. So if we have either A is odd or B is odd, then we could have the case where A is odd and B is odd, or A is odd, B is even, and A is even, or B is odd. So there are several cases that can fit the criteria for an either or statement. So that's exactly what we're going to take a look at today. And again, this is something that you use a lot of times when there are multiple possibilities for the truthhood of an entire statement. So let's go ahead and look at our first statement here. So we want to prove that if either A is odd or B is odd, then this expression a squared plus ab plus b squared is odd. So before I even begin this proof, I need to make sure that it's actually true. So a lot of you were asking, if there is a contradiction, or be careful using the word contradiction. If there is a counterexample going on, should I bother proving it? No. The answer is no. If you find a counterexample, you are going to disprove this. So let's just even see if this case is even true before we even begin. So it's saying if either A is odd or B is odd. Well, let's just say they're both odd. Then we have, let's let A equal 1, B equal 3. So then a squared plus ab plus b squared, that would be 1 squared plus 1 times 3 plus 3 squared. Well, that'll be 1 plus 3 plus 9. That'll give me 13. So that one is true. Let's try to see, okay, what if A is even, but it's, or A is odd, but B is even? Then we have a squared plus 1 times 2 plus 2 squared, 1 plus 2 plus 4. That gives me 7. Okay, so that's also odd. What about when A is even, but B is odd? Two squared plus 2 times 3 plus 3 squared, 4 plus 6 plus 9. That gives me 19. Okay, so in all of these three separate cases that meet the definition of either A is odd or B is odd, we see that the expression here is odd. So that tells me, okay, I haven't found a counterexample yet, so I have a good feeling that this is going to be true, so let's go ahead and proceed with the proof. So when we do proof by cases, it's essentially a type of direct proof, but we are using all these different possibilities of the if statement so that we can show that in every single case, the whole proof works out, it's true, so that the whole claim must be true. So let's go ahead and just start with the first one that we have here when both A and B are odd. So we want to prove either, assume either A is odd or B is odd. So our first case here is when let's say assume both A is odd and B is odd. So we've made an assumption, so we can hit this with our definition. So by definition of odd, there exists a J and a K in Z such that A equals 2J plus 1 and B equals 2K plus 1. So let's go ahead and start with our expressions. We have A squared plus AB plus B squared. So we let A equal 2K or 2J plus 1. Okay, so I've made my substitutions. I'm kind of running out of space for my justifications here, so I'm just going to do my justifications in red underneath the line so that I have enough space. So sub A equals 2J plus 1 and B equals 2K plus 1. So this is going to be equal to, so we go ahead and simplify here. So we get 4J squared plus 4J plus 1 plus 4JK plus 2J plus 2K plus 1. I'm running out of space quickly here, so plus 4K squared plus 4K plus 1. And if I go ahead and simplify, well, let me justify here. So we're just expanding our expression. So my, I want to simplify. However, there's one thing that I want to note here. I have 3 ones. I have one here, and one here. So if I combine those, I'm going to get plus 3. Now, my proof is that this expression is odd. So I want to end up with a 2m plus 1. So there are two things that I could do. I could simplify and get a plus 3 and then make it into a plus 2 plus 1. Or I could recognize that I need a plus 1 and only combine 2 of those terms. So that's what I'm going to do here. Since I need a plus 1, I'm going to keep it out and I'm just going to add the other 2 terms together to give me a plus 2 and a plus 1. So I tend to rewrite these in in the highest power order, so that's what I'm going to do here. So I get 4J squared plus 4K squared plus, I have a 4J and a 2J, so I get 6J plus 6K plus 4JK plus 2 plus 1. So we're just simplifying here. And then from here, I need to factor out my 2 so that I can make this into 2m plus 1. So 2j squared plus 2k squared plus 3j plus 3k plus 2jk plus 1. And then plus 1 on the outside. Factoring a 2, and then I can rewrite this as 2m plus 1, so sub m equals let's see if I can do this. Copy, paste. Excellent. Okay, so being lazy here, we're subbing that in, and so then we can say that since this quantity has neither fractions nor decimals, there exists an m that's an integer such that a squared plus ab plus b squared is equal to 2m plus 1 by our definition of odd. A squared plus ab plus b squared is odd. So again, we're going to leave this as an open square because I'm not officially done with all of this. So this is only the first parts. I do have 2 other cases. So I'm going to go back to my front page. So we've checked this off here. So let's do the case where A is odd but B is even, because that does still hold true since at least one of them is odd for our either statement. So our second case is going to be assume A is odd and B is even. So by definition of odd, there exists a j, that's an integer, such that a equals 2j plus 1. By our definition of even, there exists a k, that's an integer, such that b equals 2k. So let's look at what we have going on. So if I have a squared plus ab plus b squared, I sub in 2j plus 1 for a, 2k for b, then I can go ahead and simplify. Or rather expand, not simplify. And if I look at this, I don't have any like terms, so I don't have anything to simplify. So I can go ahead and factor out a 2 while leaving this 1 on the outside so that I can say that this expression is is odd. So I can just factor a 2, but leave that on the outside. Factor actually, so 2j squared plus 2j plus 2jk plus k plus 2k squared, and then leave that 1 on the outside. So 2m plus 1 here. Let me make sure I don't forget my justification statements. So now, so since, again, let me be lazy here. That's going to copy that p, but that's fine. Great. So since this expression has neither fractions nor decimals, there exists an m that's an integer, such that our expression a squared plus ab plus b squared is equal to 2m plus 1. So by our definition of odd, a squared plus ab plus b squared is odd. So again, we have proven our second case. So I'm going to just leave an open square because we're not officially done. So we just have one more case to look at. And so I have shown that we have, we've shown this, so we're good to go there. So let's go ahead and take a look at this one when A is even but B is odd. So that's our last case that meets, that holds the expression either A is odd or B is odd, that would make this true. So our last case, so assume A is even and B is odd. By our definition of even, there exists a j, it's an integer, such that A equals 2j plus 1. Nope, that is not our definition, just 2j. So then, by definition of odd, there exists a k, that's an integer, such that b equals 2k plus 1. So this is our definition of odd here. So now this is our final piece here. So we can have our expression a squared plus ab plus b squared is equal to 2j quantity squared plus 2j times 2k plus 1 plus 2k plus 1 quantity squared. So our justification, we sub a equals 2j and b equals 2k plus 1. So now we can expand, so 4j squared plus 4jk plus 2j plus 4k squared plus 4k plus 1. And so now, again, we only have 1 plus 1, so and then there's nothing else to simplify, so we can go ahead and just factor out our 2. So, and leaving this plus 1 out, since we're trying to show that this expression is odd, we need a plus 1. And then we can go ahead and sub in m for this expression here. Nope, won't let me copy it. Okay, so since 2j squared plus 2jk plus j plus 2k squared plus 2k has neither fractions nor decimals, there exists an m that's an integer such that a squared plus ab plus b squared is equal to 2m plus 1 by our definition of odd. A squared plus ab plus b squared is odd. Okay, so that is our last case to show. So our final conclusion for all of this is, having proved a squared plus ab plus b squared is odd in all relevant cases, we may conclude that if either A is odd or B is odd, then A squared plus AB plus B squared is odd. And that is our final of our proof here. So again, this proof by cases, we really know that we need to do this because we have an either or statement in our if statement. We also could do this if we had an and statement in our then statement and we use the contrapositive. And so if we kind of did two proof methods in one where we did the contrapositive and then negated the then and it turned it into an either statement or an or statement, then we would need to do cases inside the contrapositive. So some of these proof methods can be combined into each other, so it's not just in isolation. So sometimes you might have to do the contrapositive to prove something, and then there's a proof by cases inside the contrapositive. That is a total free, there's a possibility. It's a free for all for in regards to the proofs. So if you're struggling with understanding when to use each proof method, try to just understand why we're doing the proof, and that will help hopefully bring some clarity to you. Okay, so here there is a Google form to fill out that just shows that you've watched this video in its entirety, and then tomorrow we will have a Zoom call that will hopefully answer any of the questions that you may have about proofs by cases. All right, have a great rest of your day, everyone.